Boldly going where no science show has gone before. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with me, Chris Smith, and also with Helen Scales. Hello, Helen.
Hello.
Now, coming up this week, how scientists have used a stomach parasite to retrace the first human footprints in Australia and New Zealand. Who were the first people to get there? How did they get there? And when? Those are the big questions. Also, how scientists have discovered an important role for the DNA in our genomes that we'd previously written off as just rubbish. Actually turns out to have a very important job to do. And also, why, when the stakes are raised and males are forced to compete with each other, they increase their sperm count and they also produce larger and faster sperm, at least if they're a fish. And we'll be finding out why shortly, Helen.
Thanks, Chris. And this week we're looking at the science of smart materials, including substances that can repair themselves when they get damaged, surfaces that can harness the energy in light to destroy bacteria, and we'll also be finding out why the glass of the new St Pancras station in London should never need to get cleaned.
There is a coating on the outside surface of the glass, and it's a chemical called titanium dioxide. But one of the neat features of this is it works from the bottom of the dirt outwards, and so it loosens the dirt on the material's coating by destroying the layer or contact layer of the dirt and the glass.
I suspect there are one or two worried window cleaners around at the moment, thanks to that invention. Chris?
Thank you, Helen. And always, as it is here at The Naked Scientists, if you have any feedback, thoughts, comments or questions for us, you can get in touch. Our email address, chris@thenakedscientist.com.
The Naked Scientists Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
You're listening to The Naked Scientist. Now, first this week, 2 studies published in the journal Science have found evidence from the bugs that live inside our guts and from the words that come out of our mouths that both shed light on how ancient human ancestors migrated out of Asia and spread across the far reaches of the Pacific Ocean. And that's a subject that's kept archaeologists scratching their heads for decades now. Now, Yasan Moodley from the Max Planck Institute for Infection Biology in Germany led a team of researchers who collected samples of gut bacteria called Heliobacter pylori from around 200 Aboriginal people living in Taiwan, Australia, Papua New Guinea and New Caledonia. Now, these parasitic bacteria live inside the guts of around half of the people in the world, and it can lead to things like stomach ulcers, and it's genuinely people who don't have access to modern medicines who still have these bacteria. Now, they're only found inside human beings, so we think that our ancestors carried them around the globe inside their stomachs, and as they went, the bacteria mutated and evolved into different strains as they went along their way. Now, by sequencing the DNA of these gut bacteria, Moodley and his team discovered 2 new strains. The first one called HP Sahul, and they think that that split off from Asian ancestors around 30 to 40,000 years ago, with the people that came out of Asia, moved down through Indonesia, which at the time was actually a land bridge, because sea levels were much lower then. There was an ice age going on. There was a lot of water locked up in ice on the ice caps. So there was this bridge coming through to Australia and Papua New Guinea, which together formed a single landmass called Sahul, which is the name of this particular type of bacteria. A second strain, they think, called HP Maori, indicates a much later, much more recent influx of people, and this time from Taiwan. The idea here is that the people with this other strain of bacteria moved down south from Taiwan, first to the Philippines. They then got as far as Papua New Guinea, and through some sort of stops and starts, really, they got their way eventually towards Polynesia and New Zealand. Now, a really exciting thing is this other study that's actually come up with a very similar story, but looking at something completely different. Not at the stuff that grows inside us, that lives inside us, but the languages that we use. Now, languages have been used for a long time to help unpick the past, because rather like mutating bacteria, languages also change over time, and they can be used to trace relationships between groups of people in different parts of the world. Now, Russell Gray from the University of Auckland in New Zealand and his team analysed the relationships between 400 Austronesian languages that are spoken by tribes all across the Pacific. And he focused on words that are really similar between those different languages. And these are words called cognates. Do you know what a cognate is, Chris?
No, I'm not cognizant of the meaning of a cognate language.
In this sense, these are words that sound the same. So, say, for example, the word star in English. In Italian, that's stella. It's sterna in German, stare in Dutch, estrella in Spanish, and so on. So these all have very similar
Tina
connections.
Turner, surely.
Huh?
Rod Stewart?
Oh.
Tina Turner? They're stars, aren't they?
Oh, I see, Chris. Yes, indeed. It's all coming back to a very similar word, and it shows basically that those languages have all got some kind of common connection, whether you're a star or not. But this team basically took a huge amount of computing power to make all these analyses of 400 languages, looking at comparing different words between them. And they found, similarly, that there was this likely migration out of Taiwan around the same sort of time, about 5 millennia ago. Again, in fits and starts, so it seems that people were developing their ability to make boats and to cross really huge areas of sea to make their way around the world. So really, it's amazing to think that there are messages from the past hidden inside us, both in the words that we speak and in the bugs that live inside our stomachs.
Yes, it's incredible to think the genetic legacy of your ancestors lives on in you, not actually in you directly in your own DNA, which of course it does, but in the bacteria that you're harbouring too. Now, talking about DNA, there's also been an amazing discovery this week announced from scientists at the University of Edinburgh. They've got a paper in the journal Molecular Cell. This is David Tollery and his colleagues. And they have discovered the function of a whole load of DNA that's in our genomes, which we had previously written off as junk. Because when scientists sequenced the human genome with the Human Genome Project, one of the startling findings to emerge was that we actually had far fewer genes than people thought we would need. In fact, the average human probably runs on about 25,000 genes, which means, inauspiciously, we've got fewer genes running us than a rice plant. Yet we're pretty complicated organisms, so how do we manage that? Well, what they did was to look at yeast, because yeast are very similar cell types to the cells we find in our own bodies, so they're a useful, easy, very rapidly growing study subject, very easy to look at. And what they found is that although there are these big sequences of DNA that don't code for anything, they don't have genes in them, they still make chemical messengers. These are a kind of RNA molecule. And what these chemical messengers do is to manipulate the action of the genes. So what they found is that if they mutated or changed or removed some of these intergenic sequences, these non-coding regions, they found that the activity of other genes changed. So far from being junk DNA that does nothing, this junk DNA actually very carefully and accurately controls the level of activity of other important genes that keep your cells running. And why this is important and how it works is that it's all down to how DNA is packaged in cells. Each cell in the body contains about 2 meters of DNA. So with something that big, you can imagine if you had a ball of wool 2 meters long and a cell which is smaller than the head of a pin to pack it into, if you weren't very careful how you wound it up, you'd end up with a hell of a mess on your hands. It wouldn't fit. So the cells get around this problem by very accurately and precisely condensing DNA down into a very compact form called chromatin. And the problem with compactifying the DNA in this way is that it makes some of the genes hard to get at, unless you add chemical markers or tags onto the genes that keep them active. And that's a bit like you bringing things that you use a lot to the front of your cupboard so you can reach them easily, and the things that you use less you put at the back. So what they found is that these non-coding RNAs can manipulate the additional removal of chemical tags called methyl groups or acetyl groups from the proteins, the histones that DNA gets wound around, and this affects the expression of genes. So all that junk isn't really junk at all.
So understanding the junk is going to take us a step closer to understanding how our genes work. That's fantastic. Well, when it comes to being a male fish, life can be tough. When the lady in your life gets around a bit and mates lots with other males, it means that to make sure you produce lots of offspring, you have to compete with all the other guys on the scene. And more specifically, your sperm has to be up to the job. Now a team of researchers led by John Fitzpatrick from the University of Western Australia have shown for the first time in the journal PNAS this week that when male fish have to compete with each other on a daily basis for a chance to mate, their sperm evolves to be bigger, more abundant and faster. Now, when polygynous fish mate, a female lays eggs and the males then rush in and add their sperm, lots of them all together, and hope that they will get there first before someone else. Now, for a long time, biologists have suspected that polygynous males must evolve tactical sperm that are faster and therefore much more likely to reach the eggs first. But up until now, no solid proof of that idea has been found. But now Fitzpatrick and his team looked at species of cichlid fish living in Lake Tanganyika in Africa. Now, cichlids are famous for having evolved extremely rapidly into lots of different species. Now, some of these cichlids are monogamous. They stick together with the same partner for all of their lives. And others are highly promiscuous, sharing many different partners during the course of their life. Now, the researchers went out into Lake Tanganyika and went scuba diving and caught some of these male fish from 29 different species, and they dissected them to have a look at their sperm. And they measured the sperm under a microscope and used digital cameras to measure how fast the sperm was swimming around. And they found that indeed the polygynous species with the males mating lots and lots, did indeed have larger, faster sperm than the monogamous species. They also found the first really good evidence that we have that if you've got bigger sperm, then that really is associated with faster swimming, because you've got a longer tail on the sperm, which is more powerful and can generate more propulsion. And also from earlier studies, when people have drawn up a family tree of these amazingly diverse cichlid fish, Fitzpatrick and his team were then able to work out that the ancient cichlids that first colonised the lake had very small, slow-moving sperm. And then over time, as promiscuity increased, in fact, that was how the sperm then began to evolve to be bigger and faster. So cichlid fish really are the first group of species that we've able to demonstrate this evolution of speedy sperm in polygynous species. But it's likely that lots of other things are probably doing the same thing, wherever it is that males have to make sure that they pass on their genes to the next generation.
Do you think the same's true in humans, Helen?
That's a bit controversial, actually, Chris. Sperm competition is something that some people think does happen in humans, but which would suggest that we are, maybe, in some senses, polygynous. But that's another issue indeed.
Thank you. Thanks, Helen. Well, also this week, there's an interesting paper that's been published in the Journal of the American Chemical Society, and it's all about the subject of moths. Not someone with a lisp trying to say the word moth. This is actually metal organic frameworks. These are molecules that form something that's a bit like a cage. In other words, there's a hole in the middle and you can put things into it. Perhaps you could even use them, for example, to scrub gases which you wanted to remove selectively from exhaust flues. They're quite hard to make, though, so to tell us a bit more about them, here's the author of that paper, Joe Hupp. He's from Northwestern University. Hello, Joe.
Hello, Chris. Thanks for inviting me.
Good to have you on the programme. Now, tell us, what are these moths and what's their structure? If you could zoom in with a very powerful microscope and see them, what would they look like?
Well, you would see tiny metal atoms or ions on the corners, and then rigid pillars that are made of organic molecules. Each collection of these defines a cage, but the cages go on forever. And an important property of these is that they're not just isolated cages, they're crystalline materials. If you did zoom in and looked at one of these cages, you would see a tunnel going on forever with exactly the same size cage all the way through.
So they're almost like sort of children's building blocks, but with a hole in the middle that you can connect together to make enormously voluminous containers, but at a molecular level.
That's right. The materials have surface areas that are gigantic. The largest are more than 6,000 square meters per gram. They have the lowest densities of any known crystalline materials, and they have gigantic interior volume, and some of them, they're more than 80% empty. So these tiny walls define lots of minuscule spaces. The important thing is that the space is on the size of a molecule, and that's what enables them to store molecules like hydrogen or methane for fuel, or to, as you mentioned, pull some molecules out of a mixture.
And just to add some perspective, 6,000 metres squared is as big as a football pitch, so per gram, that's incredible. So when you say that you actually make these things, you have metal atoms on the corner. So if we imagine a cube, which is the simplest structural and functional unit, you've got a metal atom on each corner of the cube, and they're connected by these organic linkers. How do you actually make these things?
They turn out to be pretty easy to make. It's just hard to make them well. You simply cook them, the organic pieces that are sticky for the metal ions, and the metal ions, a mixture for 4 or 5 days, and if everything goes right, you get crystals. What we typically do is try 300 or 400 sets of conditions, and a few of them work. So it's really a very empirical science at the moment.
How much of these things can you make? Are we talking microgram quantities? Are you talking you could actually make a reasonable amount that could hold reasonable amounts of molecules?
Well, of course, in the laboratory, we are designing these and scouting these for very specific purposes, so we only need tens or hundreds of milligrams. But BASF, which is the world's largest chemical company, has demonstrated that it's easy, relatively easy, with the right materials to make kilogram quantities of these. In fact, they've driven a demonstration vehicle across Europe where the fuel tanks are filled with methane, but what stores the methane are these tiny cavities.
So could you just explain to us how these tiny cavities are useful in storing methane? Why is it better to use a complex crystal like this than to just put a large cylinder of gas in the back of the car?
Well, First of all, I don't think you or I would want to drive a car that had a stainless steel cylinder in the back in case of a collision. The methane is much more safely stored if it's in a container that's not much bigger than the methane molecule itself. It turns out that in order to stick to the material, it has to be very close to it. So in a stainless steel tank, most of the molecules never touch the wall. So it's better to have tiny, tiny channels and have those the molecules adhere to them.
And just to finish off, Joe, can you tell us, because one of the things I mentioned that you said to me was that you could scrub out gases from flues in exhaust pipes, for example. So could you make a molecule, for instance, that has a cavity that's small enough to grab, or chemically active enough to grab one species of chemical, a waste gas you don't want going into the atmosphere, and let less harmful things go past, a kind of molecular sieve, if you like?
Yes, there's lots of interesting work on, for example, pulling carbon dioxide out of methane. One of the companies in the United States, Innovine Chemicals, spends $500 million a year doing this basically with freezers. They condense carbon dioxide to a liquid to get it out of natural gas, and the reason they spend $500 million a year on this is because, well, they can mark up the price of the gas by more than $500 million a year. But it's very energy intensive, and they would much prefer to have a material that just grabbed all the carbon dioxide and left the natural gas, the methane, behind.
Joe, thank you very much. We'll leave it there. That was Professor Joe Hupp, who was from Northwestern University in the US, talking to us about a species of molecule he's working on called MOFs, metal organic frameworks, which are viewed as a very important future molecule for containing gases or trapping molecules in tiny molecular cages.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and me, Helen Scales. There's also another way to listen to The Naked Scientists, and you can chat about the science in the show with like-minded folks at the same time, and that's in the virtual world of Second Life. We're live at 10 a.m. Second Life time every Sunday, so if you want to join us, sign up for Second Life, visit the Sci Lands, and then search for The Naked Scientists. You can drop by our lovely mansion, relax on one of our delightful sun lounges, and listen to the show.
Thank you, Helen. Now, I've got a question or a statement that was put on our forum, nakedscientist.com/forum. This is from Dent Student. It is, of course, Sunday, the 25th of January. There's a clue. He's written, a visitor was being taken around the local hospital and was walking through a ward when he came across a patient lying in a bed. The patient was sitting up comfortably but was saying, and I apologise unreservedly to any Scottish people that are about to be embarrassed by my terrible attempt at Scottish accent. Oh, stay, sweet warbling woodlark, stay, nor quit from me the trembling spray. A hapless lover courts thy lay, thy soothing fond complaining. And the guy's a bit quizzical, moves on to the next bed. There's another patient there doing a similar thing. I won't repeat the accent there. And then he goes to a third bed where it says, Bannocks o' bear meal, bannocks o' barley, here's to the Highlandman's bannocks o' barley. So the visitor turns to the consultant who's with him and says, what on earth's going on in your ward? And the consultant says, it's Burns unit. It is, of course, Burns night, so a very warm welcome to any Scottish people who are listening. I hope you have a wonderful Burns night this evening.
And I will apologise on behalf of Chris for his Scottish accent. Anyway...
I didn't think it was that bad.
Also, this week, we've had a letter from Fulton Elementary School in Maryland in the USA, and enclosed in it was a little man called Flat Stanley. Now,
a real person? No.
Well, no, apparently not. He's squashed flat, apparently, when a bulletin board fell on him. And now he takes advantage of being flat to travel all over the world.
So, yeah, thank you very much for sending us Flat Stanley. So we want to say a very big hello and a big sort of virtual wave to Mrs. Con's second grade class, especially Harrison, who has sent us Flat Stanley. Stanley's in the studio with us now, and we'll send you a picture of him with us scientists here in Cambridge. So you can then work out how you can unflatten him in the future. So thanks for sending us Flat Stanley.
Now, last week, Ben and Dave were making jelly with fruit, and this week they've raided the kitchen cupboards once again and will be making yet another sticky mess.
Hello, welcome to this week's Kitchen Science, where Dave and I are going to play with the properties of polymers and possibly make some goo out of some glue. So Dave, if people want to try this week's experiment at home, what do they need to get?
You need two main things. One of them is the white glue you often use for sticking paper together at primary school, that sort of stuff. You want sort of a cup or two full of that. And some borax. Now, this is often used to help cleaning things, especially if they're very greasy. You can often buy it in supermarkets. And then a few odds and ends of containers and a few plastic cups and a couple of spoons.
OK, so we need borax, PVA glue and some spoons. Now, borax, as you said, is used for cleaning stuff, but is it safe to handle?
It is fairly nasty stuff. It's not actually poisonous, but it will irritate your skin, and it would be very nasty if you got it in your eyes while it's a powder. So make sure you get an adult to deal with the powder itself. We're going to dissolve it in water, and then it's probably not too bad, but wash your hands after you use it and don't drink it.
OK, Dave, well, you can be my responsible adult. So what do we actually need to do?
OK, the first thing you want is about 200 or 300 millilitres of hot water from a hot tap.
OK, so we'll just grab us a bit of water in a jar. So we have some water now. What's the next stage?
So we now want to dissolve about a teaspoon of borax into this water. So put a teaspoon of water in there, give it a good stir. It might take a few minutes to actually dissolve.
OK, well, I better get stirring, I suppose. So now we have some dissolved borax in some warm water. What's the next stage?
We now want to take our white glue and add about 3/4 as much of cold water to it again. So you start off with 100 millilitres of white glue, you'll then want to add 75 millilitres of water to it.
OK, so I'll get some glue. Now this stuff just gloops its way out of the bottle that it's in. You've chosen to use the bottom half of a lemonade bottle for this experiment. Is this going to ruin what we put it in? Is it best to use something that you can throw away like that, or could you use, say, a mug?
You could use a mug as long as you clean it well afterwards.
This reminds me of making paper mache. I always used to use watered-down PVA-type glue for that.
When you mix it in, it should become a lot less thick and become a lot more sloppy. And that's basically what we're trying to achieve.
OK, so let's stir that up.
You want to get it a really nice smooth mixture, which, as it turns out, the bottom of a lemonade bottle isn't a very ideal container to do that in because of the lumps at the bottom. So I recommend using a mug or something a lot more sensibly shaped.
OK, so there you go. We're learning as we go that the shape of the bottle of a lemonade bottle is not perfect for doing this particular experiment. But we've certainly got some nice, gloopy, really quite runny PVA. It looks fairly consistent. I think you've probably got most of it mixed in.
Yeah, that's probably about right.
OK, so we have our watered-down PVA, we have our dissolved borax. Now, what's the next stage?
Well, we're going to find out what happens when you mix two solutions together. So we're going to get 3 or 4 different cups with the same amount of glue in each, and then add some borax solution, maybe starting with a teaspoon or so in the first one, then a bit more in the next, and so on. And then give them a good mix in as you do it, and keep mixing for a minute or so, and see what happens to the mixture.
Well, give this a go at home and let us know. We will be back later on in the show to let you know what happens with our glue and borax mixture.
Right, well, if you've got any white glue at home, and that's wood glue or Elmer's glue will do the job, then have a go and see what the strange sticky substance you create is. If you think you know what might happen, do let us know. You can always email us at chris@thenakedscientist.com.
We are, of course, talking about smart materials this week, and in a second we'll be joining Frank Jones. He's a researcher at the University of Sheffield, and he's working on materials that can repair themselves, and we'll be finding out the applications and implications of that very shortly. We'll also be talking to Phil Irving, who's from Cranfield University, and he's trying to work out a way of uniting various smart aspects of modern technology and making them all talk to each other, so we have a sort of more joined-up way of making modern machinery. Plus, we'll be finding out why St Pancras and the technology that new station in London is employing is a nightmare for window cleaners.
Lifting the lab coat on the world's best science. The Naked Scientists.
It's The Naked Scientists with Dr. Chris and Dr. Helen, and we're talking about smart materials this week. But got a question here from Pookie Amsterdam, who is responding and reacting to the point that Helen made about bigger sperm and stronger sperm in fish forced to compete with one another. And she's asking, does stronger sperm make stronger people, or do they just get there first? Well, the answer is that the sperm are a symptom of the fitness of the genes that make them. So if you have good genes that make a strong sperm, that gets your sperm there first. If the rest of the genes then don't make a healthy individual, then they won't have much sperm to make, and they won't make healthy sperm. So I suppose you can't really have one without the other. Helen?
Right, well, this week's show is all about new materials and systems which can tell you when they're damaged and self-heal. Now, it's kind of reassuring to think that one day your car might silently repair a scratch in the paintwork or a faulty gearbox, and that aeroplanes may repair themselves in mid-air. But we're not quite there yet. To achieve the self-sensing, self-healing goal, we need researchers from many different areas of science to work together. And later on in the show, Professor Philip Irving will be explaining how the new Centre for Integrated Vehicle Health Management hopes to bring these disparate groups all together. But right now we're joined by Professor Frank Jones from Sheffield University, who's developing materials which are capable of self-sensing and self-healing. Hi, Frank.
Hi, Helen.
Thanks for coming on the show. Now, first of all, What do we actually mean by self-sensing and self-healing materials?
Well, self-sensing is largely to do with the detection of damage immediately from the structure, and healing is the situation just like in the skin where any defects or cracks can repair themselves instantaneously. There are several attempts to do this. One is to incorporate little capsules of liquid monomer that can diffuse to the crack tip once a crack runs, just like blood. And other techniques, like the one we're trying to develop, utilises the fact that a polymer has lots of unoccupied volume, and other molecules that you can encase in the structure can diffuse through them to heal a crack when it forms. So this is the general idea about these materials.
Well, first off, what sort of damage can they actually sense? What's going wrong in materials that we really need to try and heal?
Well, we're mostly concerned with fibre composite materials such as carbon fibre reinforced resins and glass fibre reinforced resins. Well, the nature of composite failure is that you get cracks in the resin matrix which are linked between the fibres. As long as the fibres are intact, the structure is still quite healthy, but the cracks can be potentially a weak link that could lead to total failure. So what you need to do is to repair those few cracks that are in the resin and keep the structure intact over a longer period of time.
And I take it that these are very initially tiny cracks, is that right?
Well, it depends. They can spread across the whole material and just bridge all the fibres and be effectively held together by the fibres that are present. If you walk along the road, for example, and you look at the white lines by the side of the curb, you'll find lots of multiple cracking in those white lines. And those white lines are cracked because of the differences in the properties of the road surface, the tarmac and the white paint. And you get the same phenomena in composites because you've got two stiffnesses between the two materials. Basically, you've got very similar analogous situations there. You could realistically heal the white paint cracks as well.
And coming back to, you started to mention already 2 different ways that we might go about making these self-healing materials. Can we talk a bit more about that? How are we going to create these materials that know that they've been damaged and do something about it?
Well, in the case that I'm working on, we have carbon fibres which are electrically conducting. So if you measure the resistance of carbon fibre, you have an easy method of detecting whether they're damaged or not, because when the fibre breaks, the resistance will go up. But we found that in an actual composite structure, if you only got resin cracks there, the resistance actually decreases. So we can detect directly that there is damage in the matrix around the fibres. And therefore we have the opportunity to utilise the resistance of the carbon fibres to provide a mechanism of healing. So if you heat up the fibres using electrical resistance, then you have a local heat where the energy needs to be created in order to heal the resin.
And that would melt something that would then stick the material together, would it?
Well, in that sort of way, yes, I guess you're right, but it has to be a little bit more subtle than that because you don't want to lose the overall stiffness associated with the structure.
I was going to say, are these materials then as robust and tough as they were when we didn't have these systems in place to have them self-healing?
Fortunately, composite materials can withstand a fair amount of damage before they actually fail, and this is the reason why helicopter rotor blades, for example, are highly durable and last for millions of cycles in a fatigue experiment. Your other guest, Professor Phil Irving, can tell you an awful lot about that, since he's worked on fatigue in fact, car springs. He was very much involved in the development of glass fibre springs for automotive industry. And there you have a fatigue structure that lasts the life of a motor vehicle. So, yeah, these materials are good. To ameliorate the damage, it gives you an extra dimension to their life.
And just to finish up, am I right that these types of self-healing materials might have a use all that way out in space, and that there's something that might help us out there? Is that right?
Oh, I think that's a good idea because you could detect the damage remotely, and you could actually send a signal to actually tell the material to heal itself. So I'm sure there's a potential there.
You don't want to have to climb out of your spacecraft, or maybe they're unmanned, and going out and fixing any damage that occurs can be quite difficult. So if it fixes itself, that would be fantastic. Well, thank you very much, Frank. That was Frank Jones, Professor of Polymers and Composites at Sheffield University, giving us a bit of a lowdown on smart engineered materials materials that can be convinced to heal their own wounds.
Thank you, Helen. This is, of course, The Naked Scientists. We're talking smart materials, and if you have any questions for us on any aspects of those things, or you just want to say hi, you can email chris@thenakedscientist.com. Coming up in a second, we'll be finding out from Phil Irving how we can actually make more complicated systems all talk together to end up with a more intelligent way of making smart materials work together. But in the meantime, let's head down to London and the roof of St Pancras Station. Mira Sinthilingham's been down there roaming around train stations to find out how nanotechnology can keep the place a bit cleaner.
This week, I'm at St Pancras International, which reopened in November 2007 after an £800 million restoration. Now, one of the more notable features of this restoration is the glass roof covering the famous Barlow train shed. It's the first thing that caught my attention as I walked in here. At over 110 feet above street level, it has an area of more than 10,000 metres squared, using over 17,000 panels of glass. But what's really interesting, though, is that the roof isn't just made of ordinary glass. The panels have the ability to clean themselves, thanks to reactions taking place on the glass at the nanoscale. So with me here at St Pancras is Ivan Parkin, Professor of Materials Chemistry at University College London, to tell me how this self-cleaning glass works.
The self-cleaning glass works under two ways. One is due to something called photocatalysis, which is the action of light onto the surface of the glass to basically chomp away or eat up the dirt or debris that's on the surface. And the other one's due to a process known as hydrophilicity, and that is that the glass loves water, and any rainwater impacting on the surface will form a sheet and wash down any dirt in a uniform fashion.
What's on the glass to cause this to happen?
There is a coating on the outside surface of the glass, and it's a chemical called titanium dioxide. Titanium dioxide is an inorganic pigment which is widely used in a whole variety of products. Everything from sunscreens, where it reflects away some of the sun's UV rays, through to toothpaste, through to the whitener, for example, responsible for the white colour in white paints or even in paper. Titanium dioxide is present as a very, very thin coating on the outside surface of the glass. It's of a thickness of about 25 nanometres, which, to put it into context, the thickness of the coating relative to the thickness of the glass is about the same relative ratio as the thickness of a 1p piece compared to the height of the Canary Wharf Tower.
Now, how does this actually work to get rid of dirt coming onto the glass?
Well, it's a twofold mechanism. One, the action of sunlight onto the titanium dioxide will generate a species known as electrons and holes. And these electrons and holes, with a very specific property of titanium dioxide, can migrate to the surface, and they can a process known as oxidation or reduction of any organic material which is present. So effectively what the titanium dioxide does, it absorbs the UV component of sunlight, and this causes the degradation or breakdown of any organic material, dust or debris, which is on the surface of the glass, and it converts it into carbon dioxide and water. But one of the neat features of this is it works from the bottom of the dirt outwards, and so it loosens the dirt on the material's coating by destroying the layer or contact layer of the dirt and the glass.
But what kind of dirt can it actually break down? Surely not everything.
Well, that's right. It primarily works on organic dirt or debris. If you have inorganic material on the surface, then that can be a problem. So, for example, if you had a self-cleaning glass which is on a seafront hotel and there was salt spray impacting on the window, the self-cleaning glass would really struggle to remove the salt which would be deposited on the surface.
What then happens to get rid of the dirt from the glass?
Any rainwater impacting on the surface will form a very smooth sheet which will wash things down uniformly. And the reason for that is that the action of sunlight on titania also produces a surface which is very hydrophilic, which means it's very water-loving. So water loves wetting the surface. The action of sunlight generates effectively hydroxyl species on the surface. That is, there's the ability of water to hydrogen bond to the glass, and that's why it wets it so effectively.
But if it then creates this sheet of water on the surface, how does that sheet then go away?
It just runs down in a uniform fashion. So instead of getting dirt concentrated on the edges of the little rivulets or droplets, which happens, and over time it builds up a higher and higher concentration, so you're going to get a runoff pattern. The runoff pattern here is very uniform, so you can't actually notice it. Everything is washed down at the same rate. But it primarily works only on surfaces which have some form of slant. If you just had a perfectly horizontal surface, then it would struggle because there's no gradient for the water then to run off. It would then evaporate, and then you would still not clean very efficiently.
Actually, that makes a lot of sense, because looking up here at the St Pancras roof, although it's arched over, every panel of glass has actually been set at an angle.
Yes, that's exactly right. If you look at the panels, they probably have at least a 30-degree angle on any one sheet that you look at. And they're not only they're angled in an arch fashion, but they're also kind of concertinaed together in a kind of corrugated fashion, so that there is a ridge line which runs down the middle of each pair of panes of glass.
Will it then take a while, once the glass has been fitted, for the titanium dioxide to actually soak up enough energy and really kick in?
Yeah, typically it will take anywhere between 12 hours on a very sunny or very wet day, all the way through to about 24 to 48 hours to work effectively.
Now, can the properties of this coating be used for anything else as well as cleaning windows?
Yes, that's actually something we're doing some research into at University College London, and that is looking at the antimicrobial properties of these coatings. And they actually show some very spectacular properties for destroying bacteria and viruses in the environment. For example, we've shown through some work that these coatings can destroy MRSA, E. coli and Clostridium difficile, for example. So any of those bugs on those surfaces, under the action even sometimes of room lighting, can be destroyed on these coated surfaces. So it's a way actually potentially of trying to help alleviate hospital-acquired infections, which are a massive source of death and also cost for all developed countries.
So our hospitals could soon not only have constantly clean windows, but reduce the presence of superbugs as well. That was UCL chemist Professor Ivan Parkin talking to our very own Mira St Thillingham about the wonders of self-cleaning glass.
I want some of that for my house, actually.
Yeah, me
It'd be
too.
absolutely
Fantastic,
terrific.
yeah.
Had a few calls, emails and texts about our kitchen science. Just to remind you what to do, you have to get some PVA glue. That's the white stuff that you use in play school. If you've got kids, you'll definitely know what this is. And you mix it with some borax, which is the stuff that you add to your washing machine to get your washing clean and soften water and things. What happens to the glue? A few suggestions. Troy has given us a chemical equation. He says glue plus borax equals glorax plus blue. Not sure if that's right or not. And Zendo says, are we making the gooey stuff that you can make, it's almost like silly putty. It runs and shatters and falls apart. Could be. Have a go and find out. And Christopher in St James says, the sticky solution you get from mixing borax with glue is a non-Newtonian fluid that becomes bouncy when you apply pressure to it and completely runny when you hang it from your fingers. And this is because borax forms ionic bonds that form long strands of polymer in the glue only when pressure is applied. Are they right? What do you think at home? Tell us. Our email address is chris@thenakedscientist.com.
Right, well, we've also had a phone call from Steve in Wormingford, in Essex, and he says, thank you very much for all the great programmes. Well, thank you, Steve, for calling, and the cheque is in the post.
Now, it is, of course, the Naked Scientists, Chris Smith and Helen Scales. We're looking at materials that can take care of themselves this week. And so far, we've heard about the surfaces that keep themselves clean, even killing off bacteria, and polymers that can patch themselves up. But no matter how smart materials are, there will always need to be systems in place that will work with them and coordinate what they do. And Professor Philip Irving joins us now. He's from Cranfield University, where he and his colleagues have established the Centre for Integrated Vehicle Health Management. That's the IVHM. And they're hoping to put all these complex threads together. Hello, Phil.
Hi, Chris.
Welcome to the Naked Scientist. So tell us a little bit about the problems you're trying to solve. What's the big nut you're trying to crack here?
Well, the first thing that we should say is that all machinery and all structures gradually degrades when it's put into service. It develops cracks, it wears out, it starts to corrode. And the way things are at the moment, all these things have to be guarded against by having manual inspection. And it would be really very, very nice if we could get away from all this manual inspection and have something that, as you say, the material looked after itself, it detected when it was damaged, and it healed itself. And that would be really very nice.
It sounds like, Frank, from what Frank was saying, that we can do that.
We can, but that's not the the end of the story by any means. We're starting to develop these self-healing ideas for polymer composites. We've still got to worry about the more traditional materials like concrete, like metal, like aluminium, like titanium, and all of these things start to develop cracks eventually in service. And so far, the only way in which we can cope with this is by predicting at what point the structure needs repairing, preferably well before there's any danger of anything catastrophic happening.
And hence that's why Frank was saying about you and helicopter blades, because obviously if one of those goes wrong, you get potentially the wind turbine effect we saw in this country that everyone blamed on aliens. That could have been structural fatigue.
That's right. Yes. Helicopters, in fact, are one of the few examples of machinery around which has got its own damage monitoring system. It's not really a smart material because it's based on the vibrations which occur in the helicopter gearboxes. But if you record these vibrations and you subject them to fairly sophisticated computer analysis, you can work out via any changes in this whether or not damage is starting to occur, and then work out what you're going to do about it. And that's really the tricky thing, as well as any sort of prediction about how long it's going to be before anything catastrophic happens. And that's the really tricky bit.
I want to know who it was who flew around in the helicopter long enough to find out that those are the danger signals.
Well, that has been a long, hard road, and there have been a number of very nasty helicopter accidents in which it was previously noted that the gears were making peculiar noises just before something catastrophic happened.
So I guess the key then is being able to anticipate what the danger signs are before they get bad enough to compromise the integrity of the material.
That's exactly right. Yes, it would be really nice if we had a sort of map of the whole structure up there in the Star Trek control cabin, and there was a red light flashing on the outer wing, and it was saying that it was damage starting to develop there, but there were still several hundred flight hours before there was anything likely to happen that was dangerous. That's the position that we really want to be in.
I did see there was quite an interesting study being done on suspension bridges which use wires that are wound into almost like plaits, and by putting the equivalent of a stethoscope on the wire you can hear these pinging noises which are individual strands of the wire going, and this means that rather than having to open up the cable and look at the physical wire condition, you can use sound to work out when you're going to have to replace those cables. So I guess this kind of idea of monitoring is coming in, isn't it? As people realise what a difference we can make.
The technique you describe is called acoustic emission and is one of the very great hopes for future damage detection in structures and machinery. It's very, very widely researched at the moment, but the difficulty is this business that we were alluding to just a little while ago. How do you go from that initial detection of damage that's saying, yes, this is going on, but the bridge is quite okay at the moment? At what point do you need to start to contemplate taking some sort of maintenance action? And it's all to do with when and how you can actually increase your life, you can increase your availability of your structure without having any sort of risk of anything catastrophic happening. And that's a tricky thing to actually calculate.
And so what at the IVHM are you trying to do in order to make that easier?
We're trying to set up a centre which brings all the various disciplines to which are needed in this together. One of the most difficult areas is the fact that the vast majority of engineering structures and machinery like a helicopter or an aircraft, it's a very, very complex system. And I'm sure you will appreciate that if we're diagnosing a human body, translating a symptom into an actual information about a damage and what the prognosis is a very, very difficult thing to do. And it's pretty much as difficult in these complex pieces of machinery like aircraft. And this is in the centre is what we're trying to do. We're trying to bring all these different parts together to try and create effective systems which are going to detect damage in this way.
I suppose that way people find out how to anticipate there might be a problem rather than find it the hard way.
Yes, I think that's absolutely right.
Thank you very much. That's Philip Irvin, who is from Cranfield University, and he set up the IVHM, which is the Integrated Vehicle Health Management Centre. And what they're trying to do, as he was explaining, is bring together the various players in structural engineering and other kinds of engineering to make sure that we can understand what makes materials fail and predict when that might happen and therefore make a difference. This is The Naked Scientists with Chris Smith and with Helen Scales. We're talking smart materials, and if you'd like to join in, the email address is chris@thenakedscientist.com. On the way, we'll be finding out when you look at a surface and you can see 3, 5, 10, 12 objects on it, at what point do you actually have to start counting to know how many there are?
Laying the facts bare.
I say.
The Naked Scientists.
Got an email here or a phone call from June in Braintree. She says, very interesting programme today. Thank you very much, June.
Right, well, now it's that time of the week to invite Diana O'Carroll back into the studio for our question of the week. Hello, Diana.
Hello, everybody. Well, this week is all about how you count.
Hi, I'm Luke from New Zealand. Say you had 3 eggs on the table. By simply looking at them, you can tell that there are 3 eggs. You don't have to count. My question is, how many eggs or any other objects do there have to be until you have to start counting them?
So when does it go from being 1 to 3 to some more and some more?
My name is Dr. Roy Allen. I'm at the School of Psychology at the University of Aberdeen. Well, he's talking about subitizing, and subitizing is our apparent ability to instantly apprehend the quantity of a small group of objects without the need to consciously count each one individually. Unfortunately, this is a research topic which has quite a heated debate about it. A lot of people argue that subitizing as such doesn't exist at all, and that really it's just some form of fast counting which is conscious. So it's very difficult to do research into subitizing simply because you have to eliminate conscious counting. And the only way to do that is to present stimuli very, very quickly, very short periods of time, something like 50 milliseconds, and then ask people to give their impression of the quantity of objects that they actually see. So this particular person's question, it's quite difficult to answer because as long as the objects are present for a long period of time, there's always the possibility that they might also be counting as well as subitizing. So the answer to the question as such is probably about 3 or 4 in the true sense of subitizing. And we probably do this by some form of pattern recognition, that there is some correlation between quantity and particular shapes. So, for example, a triangle, 3 objects is always a triangle, or almost invariably a triangle, and that's always associated with 3. 2 objects always form the ends of a straight line.
As yet, there's no definitive answer to the science of subitizing, but it looks like, at least in terms of evolution, there was no real need to be able to instantly count how many woolly mammoths were about to rampage your camp. Then there's the problem of how to extract the ability to count incrementally from subitizing, and some of you argued about this on our forum, with Dent Student commenting that his son knew there were 5 fingers on his hand before he could add them up. Dr. Beaver posited that we can only store so many quanta in our short-term memory at once, and that this number was around 7. So from counting now to polishing, and the problem with shoes.
Hello, my name is David Walwyn and I'm phoning you from South Africa. Many years ago I was obliged to polish to a mirror finish the leather shoes and belt of a certain sergeant, and the only way of achieving the desired result was to use copious quantities of spit. My question is, why does spit enhance the shine of shoe polish? And perhaps a related question. Modern shoes don't seem to require polishing. What surface finish is applied in the manufacturing which gives these shoes an everlasting shine?
Is it still worth a bit of spit and polish? Let us know how you shine your shoes by email chris@thenakedscientist.com or join our forum of science discussion. And that's thenakedscientist.com/forum.
Thank you very much, Diana. Diana O'Carroll with this week's Question of the Week. And if you'd like to catch up with past Questions of the Week, they're on iTunes as an independent podcast in their own right. You just have to search for them. Question of the Week.
You're listening to The Naked Scientist with Dr. Chris and me, Dr. Helen. And this week we've been hearing about the incredible properties we can give to materials by very clever engineering. But that sort of painstakingly slow process doesn't really suit our Ben and Dave, though, who just like to find an excuse to make a sticky mess.
Welcome back to Kitchen Science, where we're playing with the properties of PVA glue. Now, Dave, earlier on, what we did was water down some PVA glue into a nice runny solution, and we diluted some borax, that's just domestic borax, in with some hot water. Now, you said the plan is to mix these two together and see what happens. So I guess it's time to start mixing.
Sounds about right. I've got 4 cups here, so we can fill those with glue.
Now, we've got disposable plastic cups here, but I'm sure that you can do this with a normal teacup or something, as long as you make sure you give them a thorough clean afterwards. So, Dave, how much glue are you putting in each one?
About a quarter of what we started with, really. So maybe 40 or 50 millilitres.
So now we need to add some borax.
Yeah, that's right. A different amount in each one, and give it a good stir when you've done it.
So we're going to put just under a teaspoon of our borax solution in. Well, it hasn't fizzed, it hasn't exploded, and so far it doesn't really seem to have done very much at all, Dave. Oh, hello. The glue's gone very stringy. Almost looks like you're pulling jellyfish out of the glue now.
The borax obviously hasn't reacted with all of the glue. You'll probably find that a bit more of it will set if you carry on stirring for a while, but let's go for a good 2 teaspoons.
2 whole teaspoons of our borax solution. And almost immediately, the whole thing goes a bit like a fried egg in a way, isn't it? It's got that sort of wobbly whiteness to it.
It is very, very like a fried egg, in fact. In fact, the science behind it is very like the reason why an egg fries as well.
So if Dave can ever get the spoon free of the current cup of gluey, gooey nastiness solution, then we'll try it in our last cup. We'll put a lot of borax solution in, and hopefully we'll see something really dramatic from this one. So we've put 4 whole teaspoons of borax solution into this cup, and immediately it's gone that sort of poached egg, rubbery type consistency. Okay, well, Dave has now pulled out this lump of gooey, gluey, rubbery stuff. His hands are soaked in glue, but he's almost kneading it like it's bread. It's obviously very squishy, a bit like silly putty.
It's a bit like silly putty. I don't think it would bounce in quite the way that silly putty does.
What about the science behind this? What's actually going on?
PVA from the PVA glue stands for polyvinyl alcohol. This is a kind of polymer. Polymer means a single subunit repeating again and again and again in a long string. So the molecules of PVA are very long and stringy. Now, the polymers in the glue normally are quite long, but not long enough to actually tangle up completely. So they'll tangle a bit and make it quite gloopy, but not so much that it's solid.
So that's why PVA glue is actually runny and it doesn't just set straight away.
Yeah, that's right. And when it dries out, normally you have more glue in the same amount of space, so they'll start to get more and more tangly, so eventually it will set.
Fantastic. So that's how PVA glue works normally when we're using it for sensible things, like gluing things together. But what about when we're mixing it with household cleaning chemicals and making a weird putty stuff?
Well, the borate in the borax will tend to stick bits of the PVA together. It can stick to more than one bit of PVA, so it can act to link them together. This means that the chains effectively get longer and more easily tangled up with one another, so it gets thicker and thicker until eventually you've got enough to make it so thick that it's solid.
So you're almost forcing the glue to set by causing all of these polymer chains to tangle together and really lock into one another. And that's why you get quite a solid lump out of this instead of the gooey stuff that we started with. But you said that this is a bit like frying or poaching an egg. I'm sure that's not what happens in eggs.
Again, it's all to do with polymers. Inside the white of an egg, you've got some very long proteins, which are again polymers. And normally they're kind of tied up and they don't interact with one another. But if you cook them, they denature, they change the way they behave, and they start tangling up. So they all tangle up and form a big network and form a flubbery lump.
A flubbery lump, but certainly a more tasty flubbery lump than we have here, I would assume. So obviously we use this process whenever we fry an egg or poach an egg, as poached eggs are my favourite. But do we use this anywhere else, or is this, other than eggs, really just a party trick?
It's used all over the place. One of the major ones is making car tyres. Now, natural rubber is another polymer. It's very long, thin molecules, and they will tangle up with each other, and they'll go fairly solid, but not that strong. However, if you take natural rubber and add some sulphur and cook the two up together, the sulphur acts just like the borate in the experiment we've just done, ties the polymers together so they stay stuck and makes a much stronger rubber.
And that's how you get this black, tough, reliable stuff that we put on car tyres.
Yeah, that's right. It's called vulcanisation because you often get sulphur from volcanoes. Vulcan is volcano in Latin.
Well, that's all we have for this week's Kitchen Science, but there are plenty more experiments on our website, including another way to make a different type of slime, this one that actually responds to electricity. You can find out the electric slime at thenakedscientist.com/kitchen science. But that's all for this week. We'll be back with more very soon.
Thanks, guys. That was a brilliant kitchen science, and there's a full explanation of it and lots of other experiments on the website at thenakedscientist.com/kitchen science. And there's almost certainly something that you can try with things that are sitting around your house. So have a look around.
Just in reaction to that, Nat Spirit says Christmas lights repeat and tangle up, so are they therefore a polymer? Quite funny. And Zendo said earlier on in the programme, this type of glass you're talking about, self-cleaning, could it be used on touchscreen displays? Don't see why not. Absolutely no reason. Now, I've got a present for both of you. The guys gave me a pot of the stuff they made. This is an ice cream tub. Have a go at that. See what you think of that.
Look.
Here's some for you, Phil.
It looks, at the moment, it just looks like glue, but oh my gosh.
It's quite brilliant. I mean, it's...
I've given them literally they've got a handful each of this stuff.
Frank Jones should be extremely interested in this.
It
will bounce.
Stuff.
Here we are. If I can just bounce this.
Yeah. Look at mine. Mine's really long.
Oh my God! It's actually Helen's got this at arm's length. Oops!
It just broke.
It's very stretchy, isn't it? It's incredible, isn't it? And if you then let it go, it goes back to its original shape again.
Yep, strain rate sensitive.
Incredible stuff.
Properties.
And you're bouncing all over the place. You've got.
So there you go. You can something to put in your lectures next week, Phil.
I will be doing that, certainly.
Well, I'm afraid we've run out of time. Thank you very much to Phil Irving, you heard there, and also to our other guests in the programme, Ivan Parking and Frank Jones and Joe Hupp at the beginning of the programme. And of course to our wonderful production team, Mira Senthillingham, Ben Valsler, Diana O'Carroll, Tom Simpkins and Dave Ansell. Now, next week, we're sticking with the science of the very small and interesting polymer technology and things because we're looking at the nano world and how scientists are developing new devices that can release drugs in the right places, new ways to fight superbugs, and artificial skin that's complete with sensors that can help people to feel things normally again. Join us next week if you can. Chris at nakedscientist.com for all your questions.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.